Hey everyone, so this is the third lesson of this trigonometric functions unit. So we're talking about the unit circle. We're going to look at what do our sine, cosine, and tangent functions now look like. What do those graphs look like now that we're using radians instead of degrees? So just to refresh, any point on this unit circle, so a unit circle is a circle with a radius of 1, any point on this unit circle, we can find the sine and the cosine of theta using the coordinates of that point. So sine of theta is always the opposite over hypotenuse. So that's going to be the y value of the point around the unit circle divided by our radius. Cosine is adjacent, so whatever our x coordinate is, divided by our radius. And since our radius of a unit circle is always 1, y over 1 is just y, x over 1 is just x. So the coordinates of any given point are just cosine theta, sine theta. Cosine theta is the x value of any given point around the unit circle. Sine theta is the y value of any given point around the circle. And so our unit circle, flip this over and we'll draw another bigger unit circle here. We can use some of these special triangle points that we talked about in the last lesson. So you probably would have done something similar to this last year. But we're going to have what last year would have been 30 degrees is now pi over 6 radians. What last year was 45, now we're pi over 4 in radians, and pi over 3 in radians, which was 60 degrees from last year. We can use what we found in the last lesson for sine and cosine of pi over 6. So cosine of pi over 6 was root 3 over 2. Sine of pi over 6 was 1 over 2. So the coordinates at this point in the unit circle, a point that's pi over 6 radians above our x-axis, our x value would be root 3 over 2. Our y value would be 1 over 2. So we can do this all the way around. So pi over 4, cosine of pi over 4 is 1 over root 2. Sine of pi over 2 is also 1 over root 2. Cosine of pi over 3 was 1 over 2. Sine of pi over 2 is root 3 over 2. Quarter of the way around the circle, which is pi over 2, our cosine was 0 and our sine is 1. And for our 0, that was flipped. So 0 radians, that's the point x equals 1, y equals 0. We're right on the x-axis. Now we can use what we learned about our reference angles, or our related acute angles, to keep going. So we now also know the coordinates of our 5 pi over 6. So pi over 6 short of a pi, 3 pi over 4. We're pi over 4 away from pi, and then pi over 3 away would be 2 pi over 3. And these sine and cosine values, our sine values are all positive. So for instance, cosine now is going to be a negative. We got negative root 3 over 2. Our sine value stays positive. All of these are positive. our pi would end up being negative 1, 0. We can keep going around the circle. We're going to have our tan value be positive in this quadrant. So we can similarly see pi over 6 added. We're going to be 7 pi over 6, 5 pi over 4, 4 pi over 3. And now, if we are in this quadrant, both sine and cosine are both negative. So negative root 3 over 2, negative 1 over 2 would be our coordinates for 7 pi over 6. And similarly, these would all have negative x and y coordinates as well. And then our final quadrant is our cosine quadrant. We're now coming from 2 pi, so 2 pi minus pi over 6, we're going to be 11 pi over 6. 2 pi minus pi over 4, it's going to be 7 pi over 4, and 5 pi over 6. In this quadrant, our cosine values, so all of our x values are positive, and all of our y values, because we're below the x-axis, because they're sine, and sine is negative here, they're all going to be negative. So we're going to use this to help us graph the sine function. So pull this just off. We'll use that for reference when we meet. We are going to graph, we're going to investigate the function f of x equals sine pi. I'm just going to cut the video here and come up with this chart that we're going to use and the axes, and you'll hear from me in just a second. So in order to investigate the function f of x sine theta, we're going to compare it to what we would have worked with, or what we're familiar with in terms of degrees. Make sure we can see this, yep. So 0 degrees is going to correspond with 0 radians. 30 degrees, now that's pi over 6, pi over 4, 60 is pi over 3, 90, pi over 2, 120, so we have 4 30 degrees, 4 pi over 6, or 2 pi over 3. 2 pi over 3, 135, 3 pi over 4, 150, 5 pi over 6, and 180, that's a full pi, 210, 7 pi over 6, 5 pi over 4, 240, 4 pi over 3, 270, we're now 3/4 of the way, so 3 pi over 2, 300, adding another 30, 5 pi over 3, 315, 7 pi over 4, and then 330, 11 pi over 12. 11 pi over 6, sorry. So we can look at our unit circle from before and see, oh, okay, all of our y values were our sine thetas. So sine of 0 was 0. Sine of pi over 6 was 1 over 2. And we keep going around. So 1 over root 2, root 3 over 2, 1. Sine stayed positive because this quadrant is positive. So we work backwards. Root 3 over 2, because this was our reference angle is 60 degrees, or pi over 3. The reference angle here is pi over 4, so it's going to be the same as here, 1 over root 2. And 1 over 2 back to 0. Now as we work down, now we're in the negatives. So we're going to be negative 1 over 2, negative 1 over root 2, negative root 3 over 2, negative 1, back towards 0. Our y values are getting higher towards 0, negative root 3 over 2, negative 1 over root 2, negative 1 over 2, and we get back to 360 degrees, we'd be back to 0. So some of these are a little hard to graph. We have square roots. We don't really know exactly what that would be off the top of our head. So we're going to plug these in the calculator and get decimal values. 0, this is 0.5. 1 over root 2 is about 0.71. Root 3 over 2, 0.87. 1, 0.87, 0.71, 0.5, back to 0, negative 0.5, negative 0.71, negative 0.87, negative 1, negative 0.87, negative 0.71, negative 0.5, and back to 0, back to our 0 or 360 degrees, one full rotation around the circle. So we can use this to help us graph. So at 0, our x-axis is our angle in radians, or I guess we can just write theta. Keep it a little simpler. It's our theta axis. This is unitless. I guess they're both technically unitless. We can plot these points. So degrees is, we're at 0 radians, our function's at 0. Pi over 6. Pi over 6 would be here. 1 over 2, so 0.5. Each of these tick marks is 0.2, so we'll be up here. 0.7 at pi over 4. Getting close to 0.9 at pi over 3. At pi over 2, we're at 1. And we come back down. To 0. And we can keep filling in. So we're 7 pi over 6, sorry, we're at negative a half. And we keep going down till at 3 pi over 2, we're at negative 1. And now we work our way back up. 5 pi over 3, we're at negative 0.87. 7 pi over 4, negative 0.71. 11 pi over 6, negative a half. And back to 0. So if we get a nice smooth curve, we end up with this hopefully familiar shape of the sine function. The only difference from last year is now we're using, that's not the greatest curve, but now we're using radians instead of degrees. Maybe yours might look slightly nicer. This is a nice curve. This one looks more like a V. So we want that nice rounded curve. So key points. The points we want to make sure we're including are 0, 0, we cross right through the origin. Pi over 2 and 1, pi and 0, 3 pi over 2 and negative 1, 2 pi and 0. These are the points we're going to want to draw. Basically are right along the axis of symmetry, the middle point of the sine function, and our max and min values. The points in between when we're graphing these can be a little more approximate. I'm realizing I need to move this up a little bit so you can see these key points. I apologize. Let's actually rip off this sheet. Might be able to see that a little better. These key points, these are the ones we want to make sure we're including in order to show our shape. Everything else in between can be more approximate. We need to make sure we're showing where those points are. And especially because a lot of your graphs will be pretty rough. I'm not expecting you to have graph paper at home or have the ability to print off graphs at home. So I realize that you're going to be sketching these likely on line paper. So we're just making sure we have at least the 5 points of a single cycle. The other characteristics of these trig functions that we talk about, period. And period was how long it takes to complete one cycle. So here we start at 0, we go up and return 0, but we're not quite done the cycle because now we go down and back up to 0. So from 0 to 2 pi, that's 2 pi along our x-axis. That is our period. And before that and after that, the function keeps doing the same thing. It keeps repeating that cycle every 2 pi. Equation of the y-axis, or equation of the axis of symmetry, as it's otherwise known. That's y equals 0 in this case. The y-axis is going right through the middle of the sine function. We go exactly 1 up, go exactly 1 down. So this is right in the middle of that. Maximum value. The furthest up we ever go is y equals 1. Our minimum value is y equals negative 1, and we can specify where these maximum and minimum values happen by saying, so we have a maximum at pi over 2, and we go down, we get another maximum at pi over 2 past 2 pi. So we get one at pi over 2 and 5 pi over 2, and then 9 pi over 2, and so on. So we can say that by writing pi over 2 plus the period's 2 pi, so 2 pi n, and n has to be a natural number. It's a counting number, so 1, 2, 3, and so on. Every time we add 2 pi, we get back to our maximum value. Similarly, our minimum value happens at 3 pi over 2, and again, every time we add a 2 pi. And lastly, domain and range. Well, our domain, this function keeps doing the same thing over and over again. There's no points where we can't find a value. So domain is just going to be the x an element of all real numbers. Or because it was sine theta, theta is an element of all real numbers. range is a little more difficult, but nothing you guys can't handle. Our minimum value is -1, our maximum value is 1, and x has to stay between those values inclusive. That's our sine value. Our tan and cosine values are done relatively similar. I'm going to leave the cosine value because it's extremely similar to the sine value. But we'll go through this tan value together just to refresh what the tan function looks like. So we're now looking at our function f of x equals tan x, or f of theta equals tan theta. I've already gone ahead and written in all our radian measures because we had already done that in our sine question. As for our exact values, remember tan is always our sine divided by our cos. And from what we talked about in our unit circle, this is always going to be our y value divided by our x value. So tan is just y divided by x for these unit circles. So at 0, y was 0, x is 1. 0 divided by 1 is 0. Pi over 6. 1 over 2 divided by root 3 over 2. So 1 over 2 times 2 over root 3. We get 1 over root 3. If you have any questions on that, try writing it out first. And if you're confused as to how we got that, let me know. 1 over root 2 divided by 1 over root 2 is 1, which is just going to be 1 as an approximation. Or pi over 3, we had root 3 over 2 divided by 1 over 2. We have root 3 divided by 1. 90. 1 divided by 0. 1 divided by 0. That is undefined. So that's interesting. We'll see kind of what that shape looks like in case you forget. 2 pi over 3. Again, that's this point reflected. Our cos, our x value is negative. Negative 1 over 2. Root 3 over 2. That pi over 3, that is our reference angle. So it's the same coordinates, just negative for the sine, for the cos. So cos divided by sine, root 3 divided by -1. Calculate that after. And again, all of our tan values are going to be negative here. So -1, -1 over root 3, and then 0. 180, we had 0 divided by -1. Now, -1 over 2 divided by root 3 over 2. The negatives cancel out. We just get 1 over root 3. So we're back into our positive values here. Excuse me. Root 3. And then our 1 over 0, which is our undefined. And we're going to repeat. Down here, 5 pi over 6. Again, our reference angle is pi over 3. Our cos is positive. Our sine is negative. Negative root 3 over 2 divided by 1/2. Same as negative root 3 times 2. So just negative root 3. And we can see we're getting back to the same pattern from before if we go through that. So we'll calculate our approximate values. 1 over root 3, 0.58. root 3 over 1. Root 3 is 1.73. Negative 1.73, negative 1, negative 0.58, 0, 0.58, 1, 1.73, and then again negative 1.73, negative 1, negative 0.58, 0. So we'll see what this looks like when we graph this. So we're going to graph our chart here. So at 0, we were at 0. Pi over 6. So here I have 12 boxes for every pi. So every single unit's pi over 12 because it works nicely for all three of these fractions. Pi over 6, we are at 0.58, somewhere around here. Pi over 4, we're at 1. Pi over 3, 1.73. And we're undefined here. On the other side, 2 pi over 3, so 2/3 of the way to pi. 2/3 of the way to 12 is 8. Sorry, our 8th box here, that's negative 1.73, negative 1.58, 0, 0.58, and so on. We get to that undefined point again, and we're repeating. So we can see those undefined points, those are definitely asymptotes. Just figure out weights and we can see the shape a little better. We can see this is going up and approaching that asymptote, and same thing on the bottom. We're coming up, curving towards the x-axis, and then once we cross the x-axis, we curve back up because we have another asymptote at 3 pi over 2. Again, we're going to come up, and it's going to keep repeating after that on both sides towards this next asymptote. So for our tan function, really the only key point we need is we need that 0, 0, and eventually we're going to need a pi 0. We need that point going through the x-axis. This time we have asymptotes though, so we want to include asymptotes in our tan drawings. Our period, how long does it take for us to repeat what we're doing? Each cycle, we're going from pi over 2 to 3 pi over 2. Our period now is only pi. From 2 pi, we're doing the same thing twice. Our axis of symmetry, equation of the axis, we're going right through y equals 0, and we have kind of a mirrored effect on both sides. Our amplitude, we skipped in that last one. I'm realizing amplitude of a regular sine and cosine function is 1. It means how high above that axis do we go. Here, we're going up forever. We're going towards that asymptote, so we don't have an amplitude. We can't measure an amplitude, and we can't measure our max and min. domain, any value except for those asymptotes is okay. So our theta is an element of all real numbers, but theta cannot equal, can't equal pi over 2, can't equal 3 pi over 2, can't equal negative pi over 2. So every pi every time we add or subtract pi. And so we say n is an element of all integers. Integers, you're very familiar with the set denoted by this r with the double bar. That's all real numbers. Z with the double bar is any, I should have given myself a little more room here. It's any integer. Positive or negative, including 0. So any integer adding or subtracting to that is okay. Now range, this time our range is an element of all real numbers. We can go as high as we want, we can go as low as we want. There's no restrictions, no holes, no asymptotes, nothing. We cover all values in the y-axis. So that's the end of this lesson. Just a quick overview of your sine and tan graphs. The cosine graph, I'll leave to you. I'm hoping that you all remember the cosine graph. And if you do not, you can go through the same process we just did using the unit circle. And remember, your cosine is all your x values there. So I'll end this lesson off here. Have a good rest of your day, and you'll hear from me again soon. Bye.